Welcome everybody to the Euro online seminar series on operational research and machine learning. We have the pleasure of having today Rubén Ruiz, who is the principal applied scientist at Amazon Web Services and full professor of statistics and operations research on leave of absence at the Polytechnic University of Valencia. His interests in research include scheduling and routing in real life, as well as cloud computing scheduling. He is a very prolific co-author with more than 100 papers in international journals. And his research has also been recognized by the Royal Academy of Sciences of Spain. In terms of service to the community, he has organized major events as the Euro conference in Valencia a few years ago. And in terms of services in editorial matters, he is the editor-in-chief of the Operations Research Perspective Journal, and he's a co-editor-in-chief of the European Journal of Industrial Engineering, and a member of many editorial boards, including European Journal of Operational Research and Computer and Operations Research. We are very happy to have you today here, Rubén. So Rubén is going to give a talk. If you have very urgent questions, please put them in the chat. If not, we will have a Q&A session at the end. Thank you so much for coming today.
Thank you very much, Dolores. I really appreciate the invitation, and I am honored by the chance I have to talk a little bit. I see a lot of friends, so hi everybody. Not enough time to say hi to each one. So I'm going to talk about what I'm trying to tout across the discipline as a more pragmatic view about OR. This follows up from a presentation we did, also introduced by Dolores in the last Euro meeting. And I'm just going to elaborate on that because I want to insist on the message that I think it's important that we open up to a more pragmatic view of the field, specifically when we want to solve optimization problems in large companies. Because this is what I'm talking about, right? I'm talking about problems of very large scale in settings that change very, very, very fast. So you just don't have the time to go into a lot of detail and a lot of research, and you need to produce results fast. So the agenda of the talk, I'm going to talk a little bit about everything we know already. Everybody knows that there is a gap between the theory and the practice of operations research. Then I will explain why, through several examples and several results, why focusing on optimality is moving us away from results in practice. And then I'm going to show examples and tools that we can leverage in order to close this gap and to successfully model and solve very large and complex problems with ease, so that we can get back to the spotlight that we are, in my opinion at least, slowly losing up with respect to other techniques. So let me address this optimality gap. This is not just me saying, right? There is this gap has been recognized in the literature for a very long time. Here we have a paper from 1993 in operation research, but it's not the only one. And today it is very common for industries to use machine learning, generative AI, all kinds of tools and techniques based on AI, and not that many companies are actually using OR right now, at least not so clearly. So for example, this is another paper reassessing the scope of OR practice. And I have highlighted some parts of this abstract because it clearly resonates with my feelings about the field, right? Like OR needs to get closer to industry. I'm not saying that no one in OR is getting closer to industry. That's not true. I'm obviously generalizing as a whole, the whole field. If we take an average, well, undoubtedly we are leaning more on the theoretical than on the practical side. The gap between theoretical research and practical development has been recognized. And also this sentence, right? OR is become marginalized in some context. In my experience, for example, in Amazon, leadership doesn't really know what operation research is, but everybody knows what AI is. And everybody's asking me if we are using AI. Nobody is asking me if we are using OR. I think that's very symptomatic. These are not the only two papers. There is a lot of papers. I was actually doing a literature review a few months ago, and I found more than 60 papers that actually criticize or highlight or discuss the different aspects of this gap that we have between theory and practice. So this is my personal opinion, but I think OR has biases. And one of the biases is that we have, as a field, we have a marked preference for methods that have optimality guarantees, right? We always prefer an algorithm or a model that we use with we solve with a solver that guarantees that we are going to be obtaining the optimum solution for a given model that represents a reality that we have modeled. And adding problem-specific knowledge is something very valuable for papers. Like if you're doing a specific branch and bound, you derive a lower bound or an upper bound or a branching technique that is specific for that problem, and that results in huge speed benefits and speed gains, right? So that is something that we value a lot in our field. And reviewers and journals favor sophistication. Like usually the more complicated a problem is, the more problem-specific knowledge, the smarter the model is or the algorithm is, the better. However, in my opinion, this drifts us away from practice because it is not practical for every single different problem that we find in reality. It is not practical to have an ad hoc, specifically tailored algorithm or technique for that specific problem. That is just not practical because there are many other aspects that are very important in practice. For example, maintainability. Who is going to maintain that algorithm that has to work in production? How flexible is that algorithm? Can I change something? How much of an effort I'm gonna need if I need to change something? This can be summarized in simplicity and speed of delivery, because if it is not maintainable, if it's not flexible, you're not going to move fast enough. And problems in practice move very fast. So those things are very important. And no company is ever going to sacrifice maintainability, flexibility, simplicity, or speed of delivery for an optimality gap. They will always prefer a flexible and simple solution with a small gap, small, obviously, not large, over a very complex algorithm that has zero gap. And to be honest, what is optimal in reality? When a lot of the data that we use for the models are approximations or forecasts. And let us not forget that we're modeling. We are not solving almost ever the real exact problem that we have. We are solving already a model, an approximation of the reality. And that model has approximated data. So in my opinion, optimality in this context is not as important as we think it is in the field. So I call for more pragmatism. I call for doing things simple so that we can use them. And the problem is that when you work with our scientists, even at companies, they always think about the composition, they always think about stages, they always think about the very complex algorithms, because they don't know any better. And if we don't step up, at some point, we will have to start doing Gen AI, because we are being replaced. So I think it's the question that I'm asking the audience is it a time to be more pragmatic? Let's see if I can convince you that optimal and complexity, because I think optimality in large scale problems brings about complexity, is the enemy of just good enough. Let me use an example. This example is the traveling salesman problem. This is a problem we all know very well. Actually, I'm going to skip it because this is a very, very, very select audience I see in the list. I don't need to explain this. Let's just go directly to the model. Okay, so we want to visit a number of nodes or cities if you want, and we have to make a tour, right? So usually the variables are binaries and represent the arcs of this connected graph that we want to traverse. So xij takes value 1 if you go from node A to node J, right? And 0 otherwise. Cij is the cost of moving from I to J, and then constraint group 2 make sure that we visit, well, constraints 2 and 3 make sure that you leave and you enter every node in the network exactly once. And this constraint group 4 is just one of the many ways of breaking the subtours that result in this model if you ignore these constraints. The ones that shown on the screen require the variables u, integer variables u, and are the empty set, the Miller-Tucker assembly constraints for this model. I'm using this model. It's not the only one, because this is one of the simplest to solve. So one of the many applications I like about the TSP, it's in using circuit design. If you have a motherboard and you want to insert all components in a motherboard, or could be a motherboard or any circuit board, you have to go from one component to the next. And if you follow an optimal route and visit all the components, you will be reducing the time you need to manufacture the circuit board. So this is one of the many well-known applications of the TSP. And in the screen, you have particularly a very, very big instance with 85,900 nodes. And what you have in the screen is actually a graphical representation of the optimal solution. This instance is very well known. It was studied for a very, very long time because it couldn't be solved. Obviously, with the previous model formulation, we will need 7.3 imperial billion binary variables to solve this problem. So as said, this problem was formulated a long time ago, and it was solved in 2006 by a group of true experts, like extremely gifted and talented people. We have here for David Alpegate, Kel Helsgaard, William Cook. William Cook has been given, for example, presentations about TSP in Euro in Dublin. Robert Bixby, no less, than working for Ciplex for years and founder of Urobi. So yeah, very smart people. So they basically use a very specialized branch and cut algorithm and some other techniques to obtain the optimal solution for this problem, and actually to prove that the solution they found was optimal. So the exercise I want to do now, or the exercise I did and I want to show you results, is let's try to solve this. Obviously, we are not going to pre-compute the distance matrix. We are just going to calculate from plane coordinates, because just pre-computing the distance matrix, even if it's the upper triangular or the lower triangular, it just takes gigabytes of this space. We are going to use the Euclidean distance. And what I did in this in this evaluation, I took the latest simplex and Groovy versions, and I solved the previous model formulation that I showed on the screen. I then took the well-known Concord solver, which is a bespoke solver, which actually also uses simplex as a subroutine, but it's a specialized open source branch and cut algorithm that you can use to solve the TSP. And then I also took the link kernel and heuristic. It's I think it's one of the best known TSP heuristics. So as you can see, the two solvers in their last versions, they went out of memory after 10 hours. This is expected because the problem is huge and they couldn't give any solution. Concord also failed with out of memory because it's a branch and cut. At some point, it generates far too many nodes. But in stark difference with the other two solvers, it was able to produce, before failing at almost 2000 seconds, it was able to produce a feasible solution with a gap of just 0.7%. Link kernel is much faster. It just needs 25 seconds to produce a very good solution, 1.52. Okay, so what does this have to do with what I'm saying at the beginning? What this has to do with pragmatic OR? Well, math and ad hoc solvers is not everything we can do. We can add heuristics or meta-heuristics, and there is a world out there. You can use libraries, repositories, everything. I'm not a very good friend of using libraries and bespoke algorithms because, again, if you change the problem a little bit, a TSP library might no longer work. Actually, Concord does not work for asymmetric TSP, for example. It's assuming the TSP is symmetric. So if you make a small change in whatever, a bespoke algorithm is no longer going to work in your problem statement. So that's why we like solvers, because you can express your problem, and if your problem changes, you change your model, and the solver hopefully works. So let me introduce Hexaly. Hexaly, formerly known as local solver. It's a global optimization solver. So think like just a regular solver, but it has set and list-oriented variables, which is completely different from regular modeling. It also has constraint programming, has nonlinear solvers, and has really a lot of things under the hood. As stated, it was previously known as local solver. And you will see in a minute why I'm defending this solver. I don't have any affiliation with Hexaly. I just think it's one of the ways of being pragmatic, because all the code you have in this screen, it's all the code you need to solve the TSP. For example, we create one single variable. Actually, we have one single variable, which is a list. And this list contains the number of cities or nodes in the problem. One variable. It's just a list variable. Think in memory a permutation or array of size number of cities, which will contain the indexes of the cities as in a permutation. Then we have a single constraint, only one constraint. This list has to have in the list as many positions as cities we have. So this is all we need to tell Hexaly that we have a permutation. And this is the objective function, which looks very ugly, but if you look, it's a lambda function, which is summing for all the cities. We are summing the Euclidean distance between one city and the next, one city and the next, one city and the next. And then this last one is to go back to the depot. So objective function is a bit ugly, but it's just the Euclidean distance, the cost of the tour. And then we tell the solver that we want to minimize that. We're done. We're done. We don't need anything else. So let's see how that works. I removed the solvers because the solvers didn't work. Concord and link kernel are the same results as before. And here I have two values. So same time used in Hexaly as the time Concorde failed, and also 10 hours to try to compare with the original solvers. So everybody will think that these results are very bad compared to Concorde or to even a heuristic, a link learning heuristic. But the reality is that these results are very good considering this amount of code and this flexibility. Because if I want to change the objective function, sure, fine, do it, no problem. Very easy, very flexible to change. So the conclusion is that traditional math solvers go completely out of scope, and the ad hoc heuristics and exact techniques like Concorde, the ad hoc techniques, are very sophisticated. For example, trying to adapt Concorde to variants of TSP requires PhD time effort scales because it's very, very complicated. So the alternative in this case is to try to use solvers that don't go out of scope or scale, but at the same time work, even though they do not guarantee optimality or don't even give us a gap at all. Let me give you another quick example before moving to large real problems. This is the flowchart scheduling problem in which I have worked quite a bit. We have n jobs that need to be processed in n machines, and jobs need to visit all machines in series. So we have one task per machine and job. So n times n tasks in total. So a job can only be processed by at most one machine at the same time, and each machine can only be busy with one job at one time. So solutions to flowchart problems are also permutation problems, are represented in Gantt charts. So if we have 4 machines, this is how we will process job 1. And this duration is the processing time of the job in machine 1, job 1 in machine 1. You cannot change that, that's input data. So once job 1 is finished on machine 1, you can move to machine 2. When it's finished in machine 2, you move to machine 3, and so on. So we have, for example, this sequence. The objective we want to minimize is the make span, the time at which the last job finishes in the last machine. And you can see that we start having idle times. Machine 3 here is idle because it cannot start processing job 3 because job 3 is being processed on machine 2, and it cannot start until the job is finished. And sometimes jobs also wait. For example, jobs 4 and 5 are waiting somewhere in the factory because the next machine in the series is busy with job 2. So if we just change the sequence in this problem, you can see how we can improve the make span from 622 to 291. So this is a very interesting problem because just changing the permutation results in much better solutions. So not long ago, this was published in 2023 in Inform Journal of Computing. I was working with Bachman Eddy and Bahir Rosanei on many different formulations using MIP and CP solvers for different scheduling problems. And one of them was the flowchart. The flowchart has many different formulations. I'm not going to go in detail in the formulation, but this is called the adjacency formulation or the MAN formulation from one of the many papers that, oops, writing it with a mouse is difficult. MAN, 2 N's. The MAN formulation, this is one of the many different formulations that exist for the flowchart. So you will use Cplex or Gurobi to implement this model, and you'll go about it. So these models are not that simple to implement in the solvers anymore. You already have a number of constraints. You have this very ugly big M constraints that have a very bad linear relaxation. Yeah. So again, in Hexaly, all you need is one slide. This is very similar to the TSP. And here we just define when jobs finished. So this is just a lambda function. So a job finishes when the previous job finishes, or sorry, this is for the first machine. In the first machine, the jobs don't wait because the machine is always available. So in the first machine, jobs finish one after the other. And then for the other machines, excluding the first one, so from the second machine, because, you know, computer scientists start counting at 0. When we finish the job, is the maximum between the time at which the same job finished in the previous machine or when the same job finishes in the previous machine. So this is basically computing the Gantt chart. And then the max span is the job finishing in the last machine, the last job in the sequence. So again, very simple formulation. Let's see how this goes. So I'm taking the results of the paper I showed. No, actually, I run these results again because I changed the solvers, the versions. So here I have a constraint programming formulation and a mixed integer formulation for Cplex. So Cplex has a CPU optimizer and has the regular solver. And then for Gurobi, we only have MIP as of today. And then this is Hexaly. You know, that thing, Hexaly doesn't give us a gap anymore. You don't even know if the solution is good. But we can calculate the relative percentage deviation against the best known solutions in 240 and 120. So I'm putting together two sets of instances here. So we can see constraint programming, it's not bad. The gap is very good. Relative percent deviation is not bad. It's not giving out errors, and sometimes even proves optimality. And it was able to improve two solutions. MIPs go completely out of scope again. The gaps are huge. All these errors are memory errors. They cannot solve the large instances. And look at Hexaly, 169% against this code. So you have absolutely no idea if it's optimal or not. You're just comparing against baselines. It's not giving you any errors. You cannot prove optimality. It's still improving some solutions. So if you have worked in the flow shop, you will know that 1.69 for the instances of Bayala, Ruiz, and Framillan, or the instances of Taylor, is actually not that very good. It's not competitive with the literature. I know this literature very well because I published in this problem. If you take a state-of-the-art meta-heuristics, like the one I published with Professor Stutzle in 2017, or improvements of this meta-heuristics, or even a well-known heuristic for this problem, the picture changes a lot. For the same instances, any age, it's very fast, almost instantaneous, and already gives us 3.36%. I'm using I280 greedy as a baseline. So the RPD is calculated against I280 greedy. So yeah, very good solutions. Papers published after that, they improve solutions a little bit. Good. So we will say, oh, but this is better. Sure, this is better, but this is ad hoc specific methods for this problem. If you change the objective function, for example, tardiness, or if you add sequence-dependent setup times, if you have cooling, or whatever your factory has, you're not guaranteed to be able to obtain these results if you change the problem. Actually, you might need to go back and change these algorithms line by line of code. And that is something we don't have time for, because state-of-the-art performance takes years of work. And in real companies, you don't have years. You don't have months. Sometimes you have weeks. So this is all the groundwork I wanted to show to defend the idea of being very, very pragmatic about the kind of things we do. Let me very quickly introduce you to AWS EC2, and then I will talk about the very large problems we are solving. Very quickly, AWS is just the cloud. You have services that you can use that are already available for you, Amazon Web Services. And these services go across a lot of things, from data analytics to compute, all kinds of AI, containers, databases, from slow databases to very, very quick databases, all the way up to quantum computing if you want. One of those services, it's called EC2, coming from Amazon Elastic Compute Cloud, which is just compute in the cloud. If you want to run something, or if you want to host a service, a web server, or if you want just to compute makespan for flowchart problems in somebody else's computer, you can use, for example, EC2. So instead of buying and operating your own servers and your own hardware, you basically rent that hardware to, in this case, Amazon. So you're basically trading off fixed cost and maintenance cost for variable costs when you rent the services. For example, Netflix is user of EC2. Netflix, instead of operating its own servers, rents servers in the cloud. So how do we run this? We use a concept called virtual machines. So virtual machines are little operating systems, a Windows machine, a Linux machine that runs in a server. So a big server can run many different virtual machines. So when you run something in the cloud, you are actually running a virtual machine in one of the servers. And this is where the virtual machine placement problem appears. So we call in EC2 our servers, we call them droplets because we are the cloud, you know, and we use droplets instead of the name server. So imagine a server that has 8 CPUs. We call them virtual CPUs. This is usually cores, the number of cores that the server has. And this is an instance that requires 4 CPUs. So if we place this instance in this droplet, we are using cores 1, 2, 3, 4, and we have cores 5, 6, 7, and 8 free. If we have 2 other servers or droplets, droplets 1 and 2 are identical. Each one has 8 CPUs, but droplet 3 has 14 vCPUs. And also the instances are not the same. We have this instance 1, 4 CPUs, similar to instance 4, 4 CPUs, but instance 2 needs 6 CPUs, and instance 3 needs 8 CPUs. So this capacity is free, but you can see that we are not going to be able to host any other 6 CPU instance because we need 6 contiguous CPUs in order to place this instance. And there's also no space for an 8 CPU. So a better placement would be to move the 6 vCPUs instance 2 from the droplet 2 to the droplet 6. And now we have 4 free here and 4 free here. An even better solution is to move the 2 4 CPUs instances in the same droplet. So we have a fully empty droplet and 2 fully full droplets. This gives us the most flexibility because if we don't need this droplet, we can put this droplet to sleep, which means power savings. And at the same time, we can host a new 8 CPU instance or a new 6 CPU instance or 2 4 vCPU instances in this droplet. So obviously, this is an optimization problem, and it's actually a bin packing problem, but it's a bin packing problem of very, very, very large scale. Let me go a little bit into details. So let's model this as a bin packing problem. In the bin packing problem, you have n items of different sizes, and you want to pack them into the minimum number of identical bins. In our case, items are virtual machines or instances, and bins are servers or droplets. So we can map this virtual machine placement problem into a bin packing problem very, very easily. So n is the total number of virtual machines or instances. We're going to index them by I. N is the total number of servers or droplets indexed by J. C is the capacity of the server or droplet, measuring whatever unit of interest. In the example, I was given CPUs. And WE is the size of the virtual machine or the amount of units in the capacity of the server that this instance or virtual machine needs. And obviously, in order for the problem to be feasible, the maximum required size of any virtual machine has to be lower than the capacity of the server. So the 2 sets of variables that we need We need an assignment variable, xij takes value 1, if the virtual machine I is placed in Jeffrey J. And then, since we are going to be counting servers, we have a binary, it's actually an auxiliary variable, binary variable that takes value 1 if we are using a server J or not. The model is very compact. By the way, if you are not aware of these problems or you want to get acquainted, this is, in my opinion, the best book there is, and probably the best book there is ever going to be about knapsack problems by our very, very, very well-known colleagues, Paulo Toff and Silvano Martel. So we minimize the number of servers that we use. And this constraint makes sure that we don't place more instances in a server than capacity we have in the server. And look how we are multiplying the right-hand side, the capacity times the binary variable. So if we are not using the server, the binary variable is 0, the capacity is 0, the right-hand side is 0, which means that the left-hand side is 0, which means we cannot place anything in that server. And then constraint 3 is just to make sure that every instance is assigned to exactly one server. Okay, it's a nice and compact model, but the first thing to notice is that even if this is an assignment problem, and it's quite simple, you're going to struggle in this model with a state-of-the-art solver when you go past 1,000 bins, maybe 10,000 items, and you start getting cases where even lower than that, you cannot get the optimal solution, and it takes a long time to close the tree because of symmetries. So, but then our problem is that the problem is too simplistic. We need to extend the model. For example, as we have seen in the explanation, the servers are not homogeneous in size. So this is a small change because all we need to do is to change C by Cj so that each server has a different capacity. And you would say, this is a very small change, but the vast majority of the bin packing literature is concerned with the homogeneous problem. So this very small change breaks some ad hoc existing branch and cut approaches for bin packing problems because they assume identical servers. And it is not straightforward at all to extend it to heterogeneous servers because you cannot longer count easily lower bounds, right? So yeah, this is one. And also, we just don't have only CPU. Servers have many capacity dimensions. We have vCPUs, as I explained, but we also have RAM memory. We have graphics cards. We have number of disks. We have network cards. There is a lot of resources that we need to observe. Luckily, we don't have a geometric bin packing, so this is not like placing boxes into a pallet, like a 3D bin packing problem. It's a bit more simple. Imagine we are counting only RAM and CPU. If I place this virtual machine 1 and uses 3 CPU and 2 RAM, if we were placing squares in this two-dimensional problem, this would be a valid packing. However, it is not valid because if you count the CPUs, 3 plus 2 is 5. And we only have 1, 2, 3, and 4. We only have 4 CPUs here. So it is not a geometric. We call this vector bin packing because when we place this instance, all this part of the server is used all the time. If I use 3 CPUs, I use 3 CPUs all the time. If I use 2 RAM, I use 2 RAM all the time. So this is my only free thing. I have 1 CPU and 2 RAM available, which means, let me erase all this. Which means that if I use a vector, these are my only 2 other possibilities. Placing a 1-1 machine or a 1-2 machine. So this is called the multidimensional heterogeneous vector bin packing problem. Again, the extension is not that difficult because all we need to do is to extend the capacity of each server across every dimension K and the weight of each virtual machine, again, to each dimension and to each dimension. And instead of having one constraint per bin, we have one constraint per bin and dimension. So if you go to the literature and you search for heterogeneous multidimensional vector bin packing problems, you probably find some 30-something papers in the OR literature. And this is the theory and practice gap I was talking about. You go to normal bin packing, thousands of papers, literally thousands of papers of very, very, very good techniques. You go into making the problem more realistic, and then you're alone. Sadly, for the real problem, we are not done. We have several objectives because, for example, we want to minimize what we call collocation. We don't want to place many virtual machines from the same customer or client in the same server, because if the server faults, we are going to have a more impact. We call this a spread or collocation avoidance. So we want to pack, but not pack all the instances from the same customer into the same server. Then we have combinations of virtual machines, we have incompatibilities, we have network things. For example, if instances from the same customer are related, we don't want them in the same server, but we don't want them far away because they have to communicate with each other. So they have to be in the same network spine. So the complete model has more than 70 parameters, has 3 main groups of binary variables, 20 groups of secondary variables, more than 40 groups of constraints, more than 10 objectives. And also, the problem is huge. But this formulation is very bad already, because if you have 5,000 virtual machines and 100 servers, which is a toy problem for AWS, this already needs 500,000 binary variables. Real problems have 2 million virtual machines and 100,000 servers or more. We have some regions with 300,000, even 500,000 bins. 500,000 bins. So we could go the regular operation research route and adding cards, facets, model decomposition, but there is very little hope to scale. And the resulting techniques will be complex and hard to maintain. So with Hexaly, you can use set variables. Set variables are similar to list variables, but the order is not important because I don't care about the order of instances with assigning a server. It's just a set. So I define one set variable per server. The set variable will contain the indexes of the virtual machines assigned to it. So in a 50,000 virtual machines and 5,000 servers, we just need 5,000 set variables instead of the 750 million binary variables that we would need in the standard bin packing mathematical model. For example, this constraint, which is the typical bin packing constraint to make sure that every instance is assigned to a server. It's a simple constraint, right? Well, you need one per instance. If we have 500,000 instances, we need 500,000 constraints like this. And the left-hand side is this instance assigned to every single server. So this is huge. This is a large set of constraints. In Hexaly, you can express a partition with a single operator, is the partition operator, and you say, hey, single constraint, all sets form a partition. So the array servers is an array of set variables. So this array of set variables forms a partition, meaning each index representing instances has to be in exactly one of the sets, one line of code, one single constraint. So for example, single tenancy, this is huge. Single tenancy is customers that don't want any other customers in the same server. This is due to confidentiality. This is due to some countries having, if you ask me, some backwards legislation because of security concerns. So if an instance is marked as single tenancy, it can only be in an homogeneous droplet. It's a special type of droplet, and only one customer from in that server. So single tenancy instances only share this droplet with either shared or single tenancy instances, but from the same customer. No other customer on the same instance and the same server. So let's approach this. So we can do this with two simple constraints. The sixth constraint is defined for every two instances I and I prime of different clients. So I is an instance from a given customer and I prime from another different customer. When either I or I prime is single tenancy. So if one of these, either I or Y prime are from different customers and one of the two is single tenancy, they cannot be both in the same droplet at the same time. And then I can control 7 with, if this is a single tenancy instance I, it cannot be on an heterogeneous droplet J. So this is very simple from the modeling perspective. But if we take a small real problem, in a small real problem with this many instances and this many droplets, it turns out that we will need, this is real data, we will need 110 million constraint 6 and 6 million constraint 7. So in large problems, you go very quickly out of scale. So what will we do in operation research? What did I try to do? Reformulation. I create a new variable to taint a droplet if that droplet has already a single tenancy instance, and then I create binding constraints and I create more constraints to try to reduce the size of the model. So I don't need hundreds of millions of instances, constraints anymore. And that works to some level. But then again, with Hexaly it's much better, because in Hexaly, I can use OR as an operator. So droplet is single tenancy if it has any single tenancy instance. This is input data. So are these instances in this droplet? Any of these instances is in the set representing the droplet. I do an OR. This will return true if at least there is one single tenancy instance in that droplet. And then I can use another operator, which is the distinct operator, clients, and droplet. And this will count to me how many different customers there are in a droplet, in a given solution of a droplet. And then I have a constraint, which is an OR. Either the droplet has no single tenancy, or the count is less or equal than 1. So it's either one of the two or the two at the same time. So this is much simpler, much flexible, results in a much smaller model. So if we apply all these techniques to the full model, we can compare what happens when we build this. For example, Amazon has an Express license, Express MIP solver. So here I am comparing just the model build times. When the problems are large, and this is not even that large, look at the model build times in seconds. Because building very, very, very large mathematical models is very expensive, just building them. Hexaly is much more compact. You still need some seconds, but it's not as bad. And when we try to solve this, here I'm comparing Express, Gurobi, and Hexaly in how much I'm improving the baseline, the gaps, and the CPU times. Solutions in green are known to be optimal with a gap of 0. Remember, Hexaly cannot prove optimality, so I only know they're optimal because I compare with the other two. But see, even with 1 hour of CPU time, Gurobi gives infeasible solutions some of the time, Express goes out of memory, and the gaps, or if I calculate the improvement over the baseline, Hexaly is a bit worse than Gurobi and a bit better than Express. But the CPU times are just half. And this is 1 hour CPU stopping time. If I want to solve faster, like 10 minutes, we start getting more and more unfeasible solutions, some very weird gaps. And then the improvements don't improve. But Hexaly is not really that much worse. And if I go to 1 minute, then the solvers go completely out of scope and we start having lots of problems. And Hexaly, look at that. It hasn't deteriorated a lot. It gives you a very quick solution, and the solution is reasonable. It's improving 14% what the company is doing today. That is the pragmatic result that we need, a fast, flexible, simple improvement now. So the conclusion that what can I share is, because I cannot give you full results. So Hexaly scales very well. It's actually, we have this model in production today. And in order to solve very, very, very large problem, we just shard. We break the problem into sub-problems. We solve the sub-problems in parallel, and we stitch back the solutions. Very pragmatic way, not the composition. Just chop the problem into small pieces and then go away with it. We've been able to make modifications to the model several times with very little effort that takes 1-2 weeks. Hey, we need to do this. 1-2 weeks, no more work. So yeah, as I said, this is using in production. So my conclusion is we need a more pragmatic view of OR, or at least, apart from doing all the work that we are doing, which is excellent work, we need to do more work on being more pragmatic, because a few percentage points in gap to optimal or a slightly worse relative percentage deviation from best known solutions are not really a concern for most companies. A gap of 20% is a problem. A gap of 2% is perfectly fine. However, complexity is a very real concern. OR is not used more today in industries because we are very complex. We are not flexible. Sure, if you can show me today an algorithm that gives us optimal solutions like big solvers do, and at the same time they are flexible, they're fast, they're maintainable and simple, I'm sold. We don't need heuristics. We don't need Hexaly. We don't need to be pragmatic. But that is not the case. We don't have those tools. So what I'm advocating is for being pragmatic. And this academic zealousy about optimality and doing multi-stage, doing facets, doing decomposition, doing problem simplification, which is very nice for academic papers and for advancing OR, but we have to be aware that this is one of the key factors that, in my opinion, explains the gap between theory and practice. So the message I want to put across is that we need more research on simple, easy to maintain, yet good OR algorithms if we want to have a real impact in practice. Thank you very much.
Thank you very much, Rubén, for such a nice presentation with clear messages at the very end. So to the audience, we have a couple of minutes for questions to Rubén. So please put them in the chat. And you can see that there are already reactions to your talk. So
my intention was to give 10 minutes, but sorry, I got carried away.
No. We also started a bit later. So yes.
Don't be shy. Ahmed, I see you there.
Yes, so you see that there are positive reactions to your talk.
Anyways, that's my email. If you're too shy to ask something, feel free to reach out. I don't use social networking too much, so don't send me a message over those platforms. I might not be able to see it.
Okay, so
challenges.
Julio,
yeah, challenges before the problem is properly defined. Yeah, that's a good question, Belen. Yeah. How can I bring Hexaly into my research given its black box nature? Yeah, that's true. Hexaly is black box, but aren't all solvers the same? I mean, you don't know what a solver is doing, right? You mean compared to an open source solver that you can see the code, Julia? Yeah, anyways, my 2 cents on that. We shouldn't be afraid of black boxes. There's a lot of machine learning being used in practice through PyTorch and Python, and there is a lot of people not really understanding what's going on. As long as it works, that's another way of being pragmatic. You only care about the black box if you can reason about the results you're getting, or you don't like the results you're getting. If you're getting the good results and it's flexible and it's fast, you don't really care about what's going on. I mean, I never opened the hood of my car. I know there's an engine there. I don't care about it. I just use my car. Now, Belen raises a good point. Challenges before the problem is properly defined. Oh, we could have a good full presentation about this. Here I'm assuming the problem is defined, but yeah, in real practice, the problems are all but well defined. But that's more modeling than solving, right? So that's a topic for another day. How can we decide if a problem needs an optimal solution or a good solution? Okay, I have criticized this fallacy of optimality, but if you have a model and you can solve it very fast, very quick, and you get the optimal solution, you're done. You don't need to be pragmatic. If you have a model, you put it into a solver and it solves to optimality in a time frame that is acceptable to you, you're done. You don't need to decide. However, if the solution is not optimal, you don't get to close the gap, the solver is being very slow, that's when some of the things I said today might apply. Amazon still uses the composition for network planning. Yes, it does. It does today. Some very large problems are still too large, even if you solve them heuristically. You need to decompose them. Sorry, Dolores, I'm just reading the questions.
No, just you.
How can we link between OR and machine learning algorithms? Ooh, that's a big question. That's another presentation. How have you balanced so many stakeholders and objectives? That's a good question. One of the main threads of work I have in my organization is trying to establish a hierarchy of objectives, because you cannot optimize 20 things at the same time. And not all those 20 things are as important. So we are moving from what they think is leadership as true multi-objective to lexicographical objective optimization. I don't think it makes sense to Pareto optimize more than 3 objectives. Any future of reinforcement learning in optimization? Sure. There is only good things coming out from hybridization of techniques, in my opinion. So, simplifying the solution can be obtained faster. Yeah, this is a good question. Sometimes I see this anti-pattern when we cannot solve a problem to optimality, we simplify it. I always found this very interesting. Like, this is my real complex problem. I cannot solve it to optimality, but I can solve this simpler version of reality to optimality. And my question is that your problem anymore? I know it's a balancing exercise, right? How much do I simplify? But if you start simplifying your problem, why not solve the big problem heuristically? Because optimal solution to an approximated problem is probably not better than an approximated solution to the real problem. I don't know. Food for thought.
I think we have gone through the whole chat of questions. I'm sure that people yeah, Bella has another question. I'm sure that people will contact you with more questions, and you have provided all the details there for contacting you. I think if we don't get more questions, then what we will do is, as in previous weeks, it would be nice to have a picture. Oh, yes, there is one more question from Belen.
So you target compared to the optimal. Not always, not in all cases I have the optimal solution. Sometimes I compare against the best bound or just against a baseline solution. And then is there a value of exact algorithms helping us to learn about language? Yeah, of course. But in my experience, in very big problems, there is so very little hope of obtaining that reference solution. And again, I think we over-index. Oh, well, you don't know how good your heuristic is because you don't have any gaps. You don't have nothing. That's not true. As you can expect, real companies do have very good knowledge of what is a good solution for the problem. They have business equations and they have Excel spreadsheets and everything where they know how better your solution is. And your baseline is current reality. Sure, I don't know how far from optimal I am, but is that important? Because I cannot calculate it. If I could, I would, but I cannot. So stop worrying about problems you cannot solve. Just compare against the real baseline.
Okay. So I think we have come to the end. I'm pretty sure that people will contact you with more questions. So we would like to take a picture with the audience. Those of you who want to share your camera, we will appreciate that. In the meantime, I continue talking. We would like to thank you, Rubén, for finding the time, juggling with a job in industry and trying to be as active as you are as a good citizen with all the editorial work and so on. And we know that it's difficult to find time, but we appreciate that you did today. And to the audience, next week, December 9, last talk of 2024, not last talk of the online seminar series. There are plenty coming in 2025, but next week is the last talk. So, and remember that spread the word that, you know, these sessions are recorded and we have the videos available in the website of the Euro Online Seminar Series if you want to basically listen again to Rubén or any of the speakers that we have had. So thank you so much to everybody.
Thank you very much. I really appreciate it. Take care.
Thank you. Bye.
Thank you so much, Rubén.
Pleasure is mine. See you.